Hello, ma'am. Our topic for the JA component project is uh, for using image classification of kidney diseases using transfer learning and comparing models using saliency maps. So the team members are me, Ronit Naik, 20 BI 1080, and Nihal Srivastava, 20 BI 1078. So basically, if you look onto the data set which we used, this data set was available in Kaggle, and it consists of four major classes, which are namely tumor, stone, normal, and cyst. So as we can see in this CSV file here, it consists of the image ID, the path as shown, and the class and the target as shown. Now, in our process of conducting a literature survey, we saw that many of the researchers in the existing literature surveys have used various methods of analyzing medical images. Like they have been using CNNs and other similar architectures, where their goal was to create and accurately distinguish between images containing kidney stones and not containing kidney stones. So this was the main domain in which they worked on. Some of the researchers also worked on transfer learning models such as VGG16, ResNet, or InceptionNet, etc. But the main difference between what our work is and what the existing literature survey or what the existing literature has done is that we are trying to incorporate saliency maps, which has not been done yet until now in this domain. So Nihal will go on with the code of the transfer learning model.
So, hello ma'am, I'm Nihal and I'll be going over the code that we have written for this particular project. So, as you can see, as Ronit had told, the main idea of our project is to show how saliency maps can be used in this particular domain of medical image analysis so that we understand that what a model is particularly looking into when it is doing the predictions. So we want this to be something like a metric which is used by everyone so that we know how robust and generalizable a model can be, because if we do not consider these into factor, then it might lead to many problems, because in medical domain especially it's a matter of life and death, and these things have to be considered very well so that the results are not flawed or we are not missing out into things. So I'll be going over the brief notebook over here. All of the notebooks are quite similar, and we have just used different models in each and then ran saliency maps to know what we are seeing in each of them. So if you can see here, this is just the same CSV file Ronit had showed earlier, and we are basically seeing there's not much class imbalance. There's a little bit of class imbalance, but it's manageable. And this is basically built on TensorFlow right now, and we can see that these are the images of stones or cysts and like sample images of each. So this one is basically using the inception model as the base model, which is having the input labels of 160, 160 and 3 as the dimensions. So this is an RGB image, and basically RGB, as in we also have the depth over here into consideration. So since this is transfer learning, so we'll be putting base model as trainable equal to false, since we don't want to train it, we just want to use it directly. And what we plan to do is keep a simple structure here. Take out the feature map from the base model, do a average pooling, and then simply pass it through a dense with some a little bit of two with a little bit of dense layer and drop out in between, so that we know the direct power of the uh, base model and not much something else other than that, because we are trying to test how good the base model is. So we set a base learning rate of 0.001, and we're using the Adam compiler here to run it, and we can see that we have trained it for like 10 epochs, and we can see that loss curves are also going pretty well. There's not much variation in them, so that we know it's training well. And we can also see the average validation accuracy is 86 here, which is pretty decent. It is not a bad accuracy. So if we just consider this as like a normal machine learning or a deep learning project, and we see 86, oh, this is a great one, we can go ahead with this and we use it. But the extra step that we have gone over here is to show what the model is actually looking into. So we can see here I have some basic functions which help us to like plot the images, which is like getting the input image, normalizing it and plotting it. So if you can see, this is the image out here for the tumor, and what we can see here using saliency map is this small piece of code basically helps us do that. What we do first is like pass the image through the model, get your results, and find the maximum or arg max for each row. So this is basically arg max for each row. Now for each row we take, because we want to know the impact of each pixel in the row also. So what we after that do is we basically have to back propagate and calculate the gradient for the input image itself. This is not done by default by TensorFlow. That's why we have to add this particular line here, that is tape.watch of input layer. So this basically starts watching the input layer also uh, while doing the back propagation. And then what we do is we again pass the input image through the model, get the results, and then use this max IDs to calculate the scores. Now what the thing is that we basically take this gradient and the score and pass the input image to see what this gradient of the pixel will like. Since the input layer is of 160 160, the output of this gradient will remain the same. So we are basically getting a feature map as output, and these pixels can be directly overlaid on top to see how the to see what the model is basically seeing. So if you can see all the brighter regions here, that is white regions, is what the model considers as important to make the particular prediction. So if you can see for cyst that it has these regions as particularly important while making the prediction, whereas for stone it is looking into this particular V-shaped junction, and for a normal image it is basically trying to normalize everything and like show that this is a normal image and there's not everything is of interest here. So this is basically what exactly the model is seeing, and we have done this for all of the models. So this is basically again inception, but we have added something called as pre-processing and data augmentation. This was basically to show another concept that data augmentation might not be good in case of medical image analysis, because we are artificially making images which are not generally present in the data. So that might cause harm to, like example, if you rotate an image or scale an image, that is not necessarily available in real life. So when you try to do that and do then pass your validation set which does not have it, then your accuracy will drop down, which happened over here. So this is just done to show it and prove that sometimes data augmentation is not right, or if not done properly can be harmful. After that we have the exception model here, which is the next model which we have used, and we can see that we had done pre-processing in this also to show that pre-processing might not help, and that was the case. We also use ResNet, and ResNet also got an accuracy of 94 with pretty good plots. And if you see but the thing with this was, if you look into the saliency maps, they are pretty haphazard. They are not straight or clean saliency maps. They are not well fit, and they are not particularly pointing at the tumor where it is meant to be pointed. So although ResNet has a higher accuracy, but when we look into the saliency maps, we cannot say with certainty that the model is predicting right or how it is supposed to predict. That's what we wanted to show. The last is we are using a vision transformer to show how vision transformers have come up. The library used here is PyTorch, because that's what they're compatible with, and the model which we used so again, yeah, we first loaded the dataset, and then the model which we used was Google's VIT based patch 16 model. And these are basically some initial steps we have to take to like uh, pre-process the data so that we can pass it through this model and train it. And we have set in the parameters like how long we want to train it, what is the learning rate, and stuff like that. And finally, we have trained this, and in the end, I think yeah, the validation accuracy was 98, which is very good. Then we had simply written the saliency score again in PyTorch, and this is the same code, not much of a difference here. And after that, when we plot it, we can see that these plots are a lot better. Here, if we can see, here is where the uh, cyst is, and it is directly pointing at that particular region. Here, if you can see, this is where we have your tumor, and this is where the part is bad, that is where it's pointing at. It is not like the previous images where it was comparatively haphazard. In case of normal, the intensity is in general regions where there is no problem at all. So that just basically shows that vision transformers have done a better job, and this 98% accuracy which we got here is comparatively a lot more reliable than what ResNet has provided us with. So yeah, this is what we wanted to say, that using saliency maps in medical domain can give us a lot of advantage, and we should keep doing it so that we know that the models we are using are actually right. Thank you.